This video is a introduction to a device called a laser. So the reason it's called a laser is its name actually tells you something about how it works or why it works. So the point is so here's the word laser, right? So L-A-S-E-R, and the L is for light. The A is for amplification, so that's some engineering thing. Stimulated emission is very special. This right here is extremely interesting. And then radiation is just says it's about light. We're talking about light radiation, not like beta or gamma radiation that comes from say nuclear fission. This is about light coming from atoms or even molecules or even semiconductors, but it is about light. Maybe the big words are you get amplification because of stimulated emission, right? So yeah. So basically, here is maybe a drawing of what's going on. So I have this device. It's called a laser. And you have to input energy into it. So some energy source. There must be some means of delivering this energy into the device that's called the laser, right? So we're going to send energy in. And what you get out, I'm going to draw it as a red line because the laser that I'm going to mostly talk about in a following video is a laser that produces a red beam, right? So here is the output. And it's light, right? So you have to input energy, right? You don't get anything for free. And something really cool happens inside this laser. I'd like you to notice that there isn't much organization, in a sense, for the energy source and the laser. There is quite a bit of organization. But what you get out is extremely organized. And that's why this thing's special. I'd say it's mostly special because of the underlying physics, the stimulated emission, and the fact that the output is crazy organized. Yeah. So I go on to say that the output is a very special beam of light. It's special in many, many ways. It's organized in many, many ways. It's one of the ways it's organized is the fact that it is only a single color, monochromatic, right? Mono means one, chromatic means color. It's also extremely organized in the sense that all the light coming out, right? And you know that light, one way to understand a beam of light is there's these individual photons. So not only are each of the photons the same frequency, but each of the photons has the same momentum. Crazy organized. Normally light sources, right? Like here is an old school light bulb. So there's the tungsten filament and here's the glass. But if you look at the light that comes away, the light is not all one color. It's incandescent. It's all the color, all the visible colors, plus some UV and infrared as well, right? And also its direction of travel, they're all going in different directions. You might say that it's homogeneously distributed or isotropic in space, right? All directions are the same. Here is another sense in which the light output is very special. There is a special word called coherence. What coherence means is all of the light in coherent really refers to a wave nature, or it's like most simply understood in terms of a wave nature of light. But all the light is in phase. So phase, right? Phase refers to whenever you write down a traveling wave, right? An example of a traveling sine wave looks like kx minus omega t. There is this phase angle that you can put in there, right? This phase. So one wave could look like this. We'll call it kx minus omega t plus phase 1. And another wave can be kx minus omega t plus phase 2. And you can imagine, like, coming out of here is light waves of all the phases, as well as multiple k and omega values, because k and omega help you understand the color. But the point is like, when you look at the laser's output and you look at all of the light waves that make up this beam, there is only one phase, in a sense. There's only one phase relationship amongst all the waves. So that's another thing that's very organized about the light that comes away from this laser. And then the last detail that I'll bring up is the output is polarized. So polarized refers to something about the light itself. So you know that light, so let me describe light polarization for a second. And actually, yeah, let me do this a little bit neater. So what I'll do is I'm gonna give myself some space. All right. Okay, so polarization. You know that the electric field, right, is space and time dependent for a light wave, right? This is the wave description of light. And one way we could do this, write down this function, is let's just borrow a couple of these things, right? These are the traveling waves. If we have a traveling wave of electric field, which is, part of light, we might say that there is a sort of amplitude of the field. So I'll say that that's E sub 0. But E sub 0 actually has a direction. Let's say that the wave is traveling in the x direction, right? Can you see it's kx minus omega t? So I'll put sine kx minus omega t plus some phase. And then with the amplitude though, right, this is a vector. It travels in the x, but is polarized in a perpendicular direction. So here's an example. I'm going to multiply by j hat. So j hat is the unit vector that points in the y direction. So we would say that our wave is traveling down the x-axis, right? So here I'll draw it at some moment in time. But this direction right here is actually the y. And there are places in the wave where the electric field points upwards in the y. There are places where the electric field is 0, and there are places where the electric field points downwards in the y. And we say that this is y polarized. And the thing about the light that comes away from a laser is it is polarized. This light here that comes away from a light bulb, like even a fluorescent bulb, is not polarized. Running out of space there, it's not special that way. It's not special in any ways. You might say that the light that comes from an incandescent bulb like this, the way that it's special is all of its qualities are randomized, except for the fact that all of the light wave originates roughly in the same place. It's sort of centrally originated. But then it goes out in all directions with all polarizations, all frequencies, moving in all directions, right? All phase relationships, just not special. So the laser, in a sense, is kind of like the opposite kind of light source. I only get one direction, one color, one polarization, one phase relationship. Okay, so Here's another note on a laser. The overall energy efficiency might be very, very small. And what this speaks to, let me add some spaces actually. So and I'll do it here. Okay, so the overall efficiency may be very, very small. And the idea is in our original sort of diagram, right? I've got an energy source, so I'm going to input energy into my laser, and I get an output of this extremely special light, but that output is also energetic, right? So efficiency, maybe we'll describe it with this sort of stylized E, or this Greek letter epsilon, is the power out divided by the power in. Right? So let's describe the efficiency in terms of the power. And the interesting thing is the power that comes out of a laser might be a milliwatt. So this is 10 to the minus 3 watts, right? You can buy 1 milliwatt lasers or 5 milliwatt lasers at the, I don't know about the 5, but I think you can buy 1 milliwatt lasers at your drugstore. But the power in might be something kind of crazy like 10 watts, right? So if you do this, right, if you calculate this efficiency, the efficiency is 10 to the minus 4, right? That's a very small efficiency. But what's really cool is the energy density is very high, right? Density is sort of a spatial distribution of where the energy goes. And the sense in which this energy density is very high is, we could imagine our laser. Let's draw it in red. So here's the beam. We might have, right, the power output is this 10 to the minus 3 or a milliwatt. So there is, on this little circle of area that this beam is hitting, right? Let's say this is on the target, and the target is, I don't know, some plate. But the beam, is really small. From here to here, maybe is a centimeter, something like this, right? But what's flowing along in terms of energy is a milliwatt. Right? And so what's showing up on this little 1 centimeter squared is 1 milliwatt of power. And this speaks to, you could say, is a power per area, which is an intensity, right, is 1 milliwatt per 1 centimeter squared. A centimeter squared is, in SI units, it's 10 to the minus 4 meters squared. And so this looks like, right, if you do some math, you get a 10 watts per meter squared kind of intensity. So your intense beam may not be very large, but where the beam is going, there's a lot of power showing up there. So a lot of power in a small space. That's that energy density statement, or power density. Okay, so I bring up all this, right? We have this interesting sort of physical system called a laser. It's about energy. It's about organization of energy, right? Yeah, and there's quite a lot of physics, and I hope that at this point in your education you recognize essentially a lot of these things, right? Right, I've got a traveling plane wave, right? I just drew that here. I could describe polarization with this. This is sort of a basic description of the efficiency of machines, right? Machines convert energy from one type to another. So we might be converting energy from, say, some chemical source of energy, or maybe like a, wind power, or hydroelectric power, right? So, some sort of energy source is being converted into this very special version of energy that's just a nice little super organized beam of light of one color, right? So lots of physics, lots of like details that are honestly, each detail on its own is sort of interesting. But here comes the laser. So why are we bringing this up? Here comes the laser, and it's this really tidy system that does a lot of physics and a lot of interesting things all in one little bundle. And why do we bring it up? The reason is because stimulated emission, right, which is the laser part, is quantum mechanics. It's basically quantum mechanical, right? So that's why we bring up the lasers, because now, because you're beginning to understand the quantum mechanics of atoms, right? The quantum energetics of atoms, yeah, you can begin to understand in a very basic way, like a first principles way, why a laser should work, right? Yeah. So this is the special ingredient for a laser. It's the stimulated emission aspect. So that's what I'm going to describe in the following video.